We are going to get into nonlinear relationships, block 6. Now, this is the last lesson in your nonlinear relationships, and then you will take a quiz. So it says another example of a relationship that is not linear comes from biology. As you watch cells divide in this animation, try to identify their pattern of division. So if you're on Agile Mind, you can press the Divide Cells button to start the process of cell division. Watch what happens to the number of cells as the number of divisions increases. So if I press Divide Cells, the one cell now turned into 2. 2 cells turn into 4. 4 cells turn into 8, or 3 cells turn into 8, or divisions 3. And then after 4 divisions, we have 16 cells. So you can see there's a relationship between the number of times the cells divide and the total number of cells. Every time the cell divides, each cell splits to become 2 cells. So every time they divided, each one divided into 2. So we're going to study the graph and the table of this relationship. Watch the graph and see what it does. When we make this graph, it's not a straight line. This graph has a curve to it. It's going up. What we should see is that the pattern in the table is very different than it was for the data in the situations we've studied in this topic so far. The graphs also looks different than the graphs you have seen. So this graph is going up with a curve. This relationship is not linear, but it is not like the other nonlinear functions we've studied so far. Each time the cells divide, the total number of cells present is multiplied by 2. Complete this table to help you write a rule that represents the relationship between the number of cells and the number of divisions. So let's complete this table. So it looks like our process doesn't have anything for 0 because we only have 1 cell, there was no divisions. The process for 1, well, we had 1 cell, or 1 division, and we multiplied that by 2, so we get 2 cells. Then again, we kept the 1, we kept the first 2, and then we added another 2. We do this because we are now multiplying what we had before by 2. So then the next one would be 1 times 2 times 2 times 2, 3 2's, which would give us 8. The next one then has 4 2's, which is then 16. If you look, the number of divisions equals the number of 2's that we have. So if we were to write a rule for this, n, what we would have is 1 equals 2 times 2 times 2, no matter how many 2's, which would give us 1 times 2 to the power n. Now notice we have an exponent here. This n means that's how many 2's we have. So what function rule shows the relationship between the number of cells c and the number of divisions n? Well, our equation is going to look something like this. C equals 2 to the power n. Now, if you notice, this one left off the 1. We can completely do that. We can totally do that because anything times 1 is the exact same thing. So the equation then would be C equals 2 to the power n. That was question 3 on your packet. Notice that you need to use an exponent to represent the pattern of constant multiplication you see in this data. This is a special kind of nonlinear function called an exponential function. So if you look in the word exponential, you can see the word exponent. If we have an exponential function, we're going to have an exponent. The cell population you just investigated began with a single cell. What if the population had instead started with 3 cells, with each cell dividing as before? What would the graph of the relationship between the number of cells and the number of divisions look like in this case? Think about what's the same and what's different in this new scenario, then sketch a graph. So this is going to answer 4 and 5 in your packet. So think about what it would change if we had, instead of 1 cell, we had 3 cells. They are dividing the same amount of time. So if we had 1 cell, it divided into 2. So if we have 3 cells, each of those cells will be divided into 2. So instead of 1 turning into 2, we'll have 3 turning into 6, and so on. Did your graph look like this? Because there are 3 cells to begin with, the y-intercept of the graph is the point 0, 3. So where we start is the y-intercept. Where we begin is our b. Because the population doubles at each division, the graph is still curved and rises fairly quickly. Every time we go up, we're multiplying the last number by 2. So if we were to complete our table, instead of 1 cell starting off, we started off with 3. After 1 division, we had 6 cells. After 2 division, we had 2 2s and 12 cells. Then, after 3 divisions, we have 3 2s, so we're multiplying it by 2 3 times. And then we would have 24 cells. Again, 4, 3 times 4 2s, and 48. N would be 3 times any number of 2s that we would want. But then it would be 3 times 2 to the power n. Any number of divisions that we could put in for n. So what function rule represents the number of cells c and the number of divisions n? Well, that is c equals 3 times 2 to the power n. The 3 in the rule is the number of cells in the population before any division has taken place, so what it started with. It represents the starting value. The 2 in the rule describes the way the population is growing. Each time the cells divide, the population doubles. So the number of cells in the population is multiplied by 2. So the 2 is how it grows. The 3 is where it started. This will be true for any of your equations in exponential. The first number is where it starts. The second number is how it grows. And lastly, looking at question 6, now we're ready to explore exponential functions in another setting. Charles C. works in a pet store. She is responsible for the tropical fish. She notices that some of the fish multiply extremely quickly. A new generation is produced each day. Use the animation to explore the increase in the populations of 3 fish tanks. Each tank has a different growth rate. So she records the population as it increases every day. She records the she records the data in a table and a graph. So here's her table, here's her graph. If we want to do 1 step, 2 step, you keep pressing the steps, and then, or we could run it, and it will go up by the number of generations each time. Look as the numbers grow. The numbers are getting very, very high. That's because it looks like if we go from 2 to 6 to 18 to 54, something's happening. There's a pattern there. So between 2 to 6 to 18 to 54, looks like they're all multiplying by 3. So I know I'm going to have a 3 in here. Now, where could this have started off? Well, the number of fish at the first generation was 1. So the number of fish would then have to be 2. So it would be 2 times 3. Then, no matter how many times they grow, it's 3 to the power, sorry, not the g, but this one, the exponent, g. Oh, I made a mistake here. Hold on, what could it be? What if instead we tried g minus 1? There we go. Now let's look and see why that worked instead. So 2 times 3 is 6, but if we put in this 2 here, it would have, so then it would be 2 minus 1, so which is 1. 2 times 3 is 6 to the power 1, that gives us 6. So that's why it works there. Now the birth rate in the second tank is 4. Press step to see the number of fish in the next generation. Press run to see how the population changes over several days. I'm just going to press run. We're going to look at what's happening here. As you can see, the population is growing by an even steeper amount. Looks like in this one, the population is starting at 2 again. We're multiplying, but this time it looks like we're multiplying by 4. Now, if we put in g here, let's see if that would work. 2 times 4 is 8 to the power 2. Well, we don't want to do that because then that would give us 64. We can't do that. I'm going to do g minus 1. And finally, the last one. This is a birth rate of 2. So it's a little bit less than what we've been working with before. We had 3 and 4, and now we just have 2. So our curve isn't as steep. This time, if we go with our same pattern, it started at 2. We multiplied, but this time our birth rate was 2. And we're going to have g minus 1. All right, finish block 6, turn that in, and then once you're done with that, you can start on the quiz if you have not already. Thanks, guys.